Hello. In a previous video I was talking about integration and substituting limits in and what happens when we've got a natural logarithm as our answer, and I was talking about using modulus brackets. What I want to do is just use this opportunity to give further explanation to that, because it didn't really seem appropriate in the middle of an example, so I thought I'd put it as an add-on point in this video here. So I've started with a graph which is drawn in front of you, y equals 1 over x, okay, and I'll just give you that simple integral then of integral 1 over x dx, and we would have the natural logarithm of, now as I mentioned we use modulus brackets. I'm ignoring the plus c because I'm going to put limits in a second, okay. So we have natural logarithm of modulus of x, okay. Now I've mentioned the reason this is because we want to substitute negative limits in sometimes. Now I'm just giving an example of that. Suppose I asked you to work out the area bounded between x equals 1 and x equals 4. Okay, there's 1 and 4, and just going to shade it in, just like that, okay. And then what you do is you'd put in limits on your integral here, see 1 and 4, and then in the integration, because we've got limits to substitute in, we put 1, 4, just like that, and then we do the largest value first, and then subtract the lowest value. Natural log of 1 is 0, so that's just natural log of 4. And that's our answer. Okay, if you can remember that, that would be great. Well, what happens if you want to find the area that's bounded between, this time, negative 4 and negative 1? And we say it in that order because negative 4, of course, is the lowest number. I'm just going to shade that area in. Now, I'm hoping you'd see that because of the symmetry of the graph, the answers are exactly the same. So we've got to surely end up with the same answer of a natural logarithm of 4. However, we need to change the limits in our working because we don't have 1 and 4 anymore. We've got 4 and 1. So I'm just going to erase this bit of working, and we're just going to hope we get the same answer, which we will do, we know, because of the symmetry of the curve, as I said. So negative 4 and negative 1 are the limits, and I'll just put them in both here and here, and we substitute them in. The largest value first, of course, so natural log of, now the modulus of negative 1, and then subtract the natural log of the modulus of negative 4. Okay, so that would give us natural logarithm of 1, which is 0, as before, and then we'd have subtract natural log of 4. And you might be thinking, well, hang on, that doesn't equal to natural log of 4, does it? Okay. Well, if you remember some of the earlier work we did in integration in year 12, you'd remember that when we have an area that is bounded above the x-axis, we usually recognise that as a positive area, because this area here would give you a positive result when you substitute the limits in. And any area bounded by the curve and the axis, if it's below the x-axis, then that would give us a negative area. So it's not at all surprising that we get negative natural log of 4. All we'd need to do is just rewrite our answer as the area is equal to natural log of 4, just taking the positive value. Part of the challenge sometimes of working at areas is recognising when it's a negative area and just taking the modulus of that. Okay. Now this would not have worked for us if we didn't have these modulus brackets around the x, because if you substitute in a value of x is less than 0, well, your calculator won't like it very much, will it? Because you can't do the natural log of a number that's less than 0. So that's the reason why we have modulus brackets when we are integrating and we have a natural logarithm as an answer. I hope that's cleared that up for you. If you do have a few more moments, let me just show you this neat little result here, which I prepared earlier. So this is a little bit more about the natural logarithm and e in calculus. So you see here the graph drawn, y equals 1 over x, and in this case we're wanting to find the area between x equals 1 and x equals e. If I say it in full, we normally say find the area bounded between the curve y equals 1 over x, the x-axis, and the lines x equals 1 and x equals e. Okay. And if you go through the working, that is when you integrate 1 over x dx and bring the limits x equals 1 and x equals e, then of course you get the natural logarithm of x. That is written as log base e, but we just write that as natural logarithm of x. And when we substitute, we have natural log of e subtract natural log of 1. As with earlier, natural log of 1 is just 0, so you just end up with natural log of e, which is just 1 anyway. So the really cool result about that is that this area here is precisely 1. Okay, I think it's really rather nice. Okay. I just want to clear something up finally. This will be the last part of the video. Something that I put in one of my early videos. Okay. Now what I mentioned as an example, it's a bit of a throwaway example, but I didn't think anything of it until I watched my video again. I sometimes watch them again, mainly just to check there's no errors in there, and so far I haven't found any. If you find any, drop me a line, because then I'll sort that out. But somewhere I put this as a throwaway comment. Okay, I did say be careful when you're integrating, you need the non-modulus brackets in case you've got a negative value in there somewhere, and I think somewhere up in limits of -1 and 1, and that's just rather worth further discussion. Now I'm hoping that if this happened in a classroom, one of you would have said, but sir, if you do that, that's rather awkward, isn't it? Because if I show you, what we're trying to find is the area bounded between these values of -1 and +1, and I'm hoping that you can see it now. We don't end up with a area that is bounded, do we? We don't end up with a finite area, because the graph is asymptotic. What that means is the curve will approach the y-axis but never actually touch it. Okay, it keeps on going on forever. So it's not effectively a shape that's bounded between lines, is it? Okay, so I thought I'd just clear that one up. Don't worry, you will not be asked to do that question. Okay, that's something for you to investigate later on, what to do when you have areas that are not perfectly bounded by curves, or when you've got a situation like this where you don't have a clear finite area. Well, clearly you could just do the same as double the integral between 0 and 1, but then the problem there is how do you get around that? Because if I just show you quickly, put in the natural log of x, and then with limits, put in x equals 1 is fine. Natural log of 1, that just gives you 0, but then what are you going to do when you have the natural log of 0? There's no getting around that, is there? Okay, so that's rather difficult. So if I thought about it more clearly, the example I'd have used on that throwaway line would have been if you have limits like -4 and -1, as I just did. But I thought I'll just clear that one up for you, just in case you were wondering. Right, that's it for now. Have a nice day.